Yes, can you hear me? Okay. All right. All right, I guess we can get started. So, as you hopefully remember, I'm talking about cosmological gravitational wave sources and really the stochastic backgrounds of cosmological origin. A couple of things to briefly review before we get before we dive in. So first, we're really dealing with very early universe, and if you remember, I showed this picture of schematic of the evolution of the universe. We're really talking about the physics that happens that's relevant for energies before or higher than the MeV scale, roughly speaking, when the universe was less than a minute old. We really don't have any observational data about that period, and there's a lot of different physical models that we could be testing there, and processes that could produce gravitational waves. So one of the what we decided to do, or what I decided to do, was to focus on one of those, which is um, for most people or many people one of the most interesting cosmological models, which is the behavior of the vacuum modes from the original quantum mechanical fluctuations in the early universe, and how they behave as the universe transitions through different phases and so on. So we went through that example, if you remember, of a pendulum that whose length increases rapidly, and we found that the number of the occupancy of, for example, the ground state increases dramatically when the pendulum is elongated. So now we're trying to do this for the early universe, and we started off by writing out the perturbation of the metric in something like a plane wave expansion. It is a plane wave expansion in the position coordinates, so e to the I k dot x is the same as before, but the time dependence, we allowed it to be more complicated than just oscillations because of the expansion. And eta here is the time, but it's the conformal time, which we'll come back to as well. And of course, this is the two polarization tensors, the plus and the cross. So the phi here are our amplitudes, and that's kind of what we're after. And we also redefined, we introduced a new variable called psi. These are dependent on the modes, k. So in general, depending on the amplitude and the direction of the mode. And when we kind of hand wave this a little bit, but from using the Einstein equation, one can show that these modes or these psi's obey this kind of an equation. And really, when you write this equation in terms of phi, it's basically a wave equation, except there's this extra term that has to do with the changing of the underlying metric or expansion of the universe. So then we said, okay, we want to find these psi's, and we want to connect them and so on in two different phases. So we said, let's say, suppose we have two phases, 1 and 2. We'll see what they are later. It could be inflation and radiation, for example. Let's suppose that little f and big F are the solutions to this equation. So in that case, since these are complete sets of functions, they can be thought of as bases of a set of functions, and you can express one of them in terms of the others, linear combinations. This is not exactly right. There are the e to the ik's and so on in here, but just to remind you, there are these alphas and betas, which we named the Bogoliubov coefficients. And then after some massaging, we could basically say, okay, if I write that down, the equivalent of this expansion in a quantum mechanical setting is something that looks like this. So instead of phi's, I have the f's now. Again, the e to the ik dot x and the polarization tensor. But I throw in the raising and lowering operators. And this is really field theory, so we're touching on that. But we don't really need anything more from field theory than this. So if you take this and this connection here, then you can relate the raising and lowering coefficients, these ones here, in phase 1, which we labeled with small a's, and in phase 2, which we labeled with big a's. So we have a relationship that looks like this, that connects the lowering operator in phase 1, okay, with the lowering and raising operators in phase 2 with these coefficients, alphas and betas. And similarly the other way around. And there was a question, I think, towards the end of Friday, is it really, are stars really on both of these? And I checked they are. So this was the correct description. So that's about as far as we got last time. I mean, are there any questions on this before we continue? Everybody okay? All right, so the next thing that we're going to do is, so we'll take this, but we're going to assume a couple of things. So for example, we'll assume that the expansion or the cosmological background metric is both isotropic and homogeneous, and that's a common and hopefully a good assumption. And if that's true, then you can basically the gravitational field cannot change the direction because that would be changing the momentum, and there would be no reason to do that if the background is isotropic and homogeneous. So these alphas then can be written solely in terms of the amplitude of k, which is also the frequency. So we can then write something like this: alpha k k prime, which are here we're writing the num with the direction dependence as well. But we can then write something like this: alpha f. F is really just the length of k, okay, and the delta k k prime, meaning we cannot change the direction of the mode. And similarly for beta. Okay. So with those changes, then let's say the lowering operator in phase B, which would look something like this. So we can write it first completely. So this would be the sum over k prime, and then instead here we have a sub b of k prime, and instead of the full alpha here, we write these delta functions. So we have alpha sub f times delta k k prime, and a similar thing for the dagger. I think this is star as well. Delta k k prime. Okay. And we can suppress some the b dependence. We don't really need it. In which case we can basically write something like this. So this would be the lowering operator in phase 2 at some frequency f. That can be written as alpha sub f times a star times a sub f, and then minus a, let's see, as beta sub f star times a dagger sub f. Okay. So the next thing that we'll do is we'll need this piece. We will also, there are some relationships that the Bogoliubov coefficients obey, and you can derive them. They're relatively straightforward. Once you write this down and the corresponding expression for a dagger, you can manipulate them and find relationships. And one of them looks like this. So the sum over k of alpha, let's see, k1k, and alpha star of k2k, minus similar thing for beta, so beta k1k and beta star k2k. This is just a delta function between k1 and k2. So if I had some two wave vectors, k1 and k2, and I wrote this kind of a sum over yet another k, this would hold. And you can basically find that by taking these, multiplying them by yet another alpha, for example, summing over another k, and kind of following through with the algebra. So if I take this relationship and instead I assume that the underlying metric is homogeneous and isotropic, then I can suppress these k's, right, and instead write the alphas. So this would look something like this. So this would be sum over k again, and then we have alpha f. Instead of this one, we'll have a delta function k1k. Instead of this one, we'll have another alpha, so we'll have alpha f squared, and then the delta function between k2 and k. And a similar thing here. So we'll have beta f squared delta k1k and delta k2k. And that's supposed to be delta k1, k2. And then if I pick the simplest case where k1 is equal to k2, then these two delta functions will really be the same. And when I do the sum, I will pick out one value of this k, which is equal to k1 and k2. So this whole sum will just collapse, and I'll have alpha f squared from the first term, and similarly beta f squared from the second term. So if I just choose k1 to be equal to k2, then this collapses to something like alpha f squared minus beta f squared is equal to 1. Okay, so that's another piece that we will need soon. Okay, so far what we have is some relationships between alphas and betas. I know it looks like there is no end to this, but we will actually pull the pieces together quickly, and it will start to make more sense, I hope. So in fact, we are now ready to start looking at the occupancy numbers, right? So we can suppose that we are in some initial in phase 1. So in phase 1, let's suppose that we are in some state n sub f. So we have occupation numbers n sub f. F here is a frequency, so at each frequency we could have some number of modes, and that will be our initial state. Okay. So what that means is that if I apply the raising and lowering operators, so AF dagger AF, which would be the same as the number operator, remember, and if we act on n sub f state, then this will pick out the number of modes at frequency f. So we'll have n sub f multiplying that same state. Okay. So that's basically what we're starting with. So this is our short pendulum. Okay, this describes it's the equivalent to the starting point with the pendulum story. Now the next thing will be the universe expands. Okay, and the expansion happens on some time scale delta t. Okay, and then we're basically going to ask, let's suppose we look at the modes. So focus on modes which are for which we can, whose period is much longer than this, right? So 2 pi f times delta t would have to be much less than 1. Okay, so you can see if I pull f on the other side, I get 1 over f, which is basically the period of the oscillation. So that has to be much longer than delta t, meaning that the expansion happens very quickly on the scale of that particular mode. Is that okay? All right. So what we want to do then is look at what happens to the occupancies in this state after we make that change. And after we make that change, we're in phase 2. So we now have to use the raising and lowering operators of phase 2, which is these capital A's, right? Okay. So the number of modes, the number of the occupancy at the frequency f is going to be given by the expected value of the state that we're starting with, so n sub f, times the number operator, which is in this case capital A dagger, capital A, and then again this state that we're starting with. Okay, so now, oops, A sub f we can write in terms of these guys, right? We have the expression for them, so let me write that out. So we have A sub f dagger alpha f minus a sub f times beta f, and then multiplying that with a, which is a f times alpha f star minus a f dagger times beta f star. And then I put in the state. Oops. All right. Well, so now I have to multiply this out, and let's look at what we get. So we have n sub f state, and then we have okay, so we'll have alpha f squared af dagger af. That's the first terms multiplying. Then we'll have let's look at the last two terms multiplying. So that will give me plus beta f squared times a sub f and a sub f dagger. So that's second term times the second term. And then I have the cross terms. So we'll have a minus alpha f star beta f, and then we'll have af and af. That's these two multiplying each other. So af, af. And then minus the other one is alpha f times beta f star times af dagger, af dagger. Okay, and then again the state n sub f. So now you look at this. Let's, for example, look at this term. A sub f will lower the number of or the occupancy number in the at the frequency f. Okay, but then the second one will do the same, and as a result, this state will be different from the bra on this side, right? So that cross product will then be just, or inner product, I should say, should then be just 0, right? So this term here changes. If we think of this as acting on the ket, this will change the occupancy numbers in that state. So when I dot it with the bra, I'll get 0. So that goes away. And for the same reason, this one goes away as well. These ones are nice, though. This is the number operator. So remember that AF dagger, AF, is the number operator. I should really call it like this. It's when I write it like this, I mean the number operator. Let me put a hat or something so it's clear that it's an operator. So when this acts on the state n sub f, it gives me back n sub f, right? So let me write it out. AF dagger AF acting on n sub f gives me n sub f times the same state back. And the other combination is related, but if I act on n sub f with this, I get n sub f plus 1 back, I think. Let me double check. Yes. Okay. So these are just the typical standard raising and lowering properties of the raising and lowering operators. So what does that mean? So I'm back here. I will have alpha f squared multiplying this here is this piece, so that's n sub f. So alpha f squared times n sub f. And then I will have beta f squared plus beta f squared times this piece, that's this one here, that's nf plus 1. All right, so that's good, but I can go one step further because I also have this relationship between alpha and beta. So I can choose whatever I want, but let's say I express alpha in terms of beta there, and I change it here. So this becomes 1 plus beta f squared multiplying n sub f plus beta f squared times nf plus 1. So we can rewrite this, and maybe I can write it here. So n sub f can be written as little n sub f. That's coming from this first term, for example. And then I have beta squared NF, and I have another beta squared NF, so I can write this plus 2 beta squared F times N sub F, and then plus a half, which would be basically this beta squared times 1 here. All right, so this is a nice result. This is basically telling me, initially I started off in a state with this many modes, okay, with this occupancy, little n sub f. After the expansion, at that same frequency f, I have this many particles, okay? And obviously everything here is positive, so the number of modes has increased, okay? This is equivalent to what we saw, for example, for the ground state of the pendulum. Now we see it for each frequency, okay, of gravitational waves. We see that those modes get amplified, if you like. Bruce tells me I shouldn't use that word, but the number of modes just increases. And you can see that if you were starting with n sub f equal to 0, then that's gone, so you're left with only beta f squared. So the number of modes after the expansion would be beta f squared, and in general non-zero. Yes, I'm sorry. Yes, absolutely. Yes, correct. Okay. Any questions so far? All right. Yes. Absolutely. I haven't done anything inflation related here yet. Yes, it's you have to change the metric. That has to happen fast enough. It will happen fast enough for some modes, right? And for those modes, there will be this effect. And it doesn't matter which two phases you choose. In fact, we'll look at that hopefully a little bit later. Yeah. Yeah. No. So Bruce has a very nice argument about this. In fact, even with the just a simple pendulum, you can show that the energy actually drops. It's basically that you're losing, you're keeping the kinetic energy. Is that correct, Bruce? And you lose the potential energy. So the total energy actually drops, and I guess you have to get that energy from the whatever is driving the change. In the inflation case, it would be the inflaton probably. But in the end, you're left with less energy, but the number of particles that you have, the number of quanta increases. Mm-hmm. Yes. Mm-hmm. Yeah. Okay. It was omega initial over omega final, right? Mm-hmm. Right. And you can then substitute, right, the energy of each mode, which would be h bar omega, F. Yes. So this will be the E final, right? And yeah. Does that answer? Yep. Not really. We won't have time for it. You mean the modes that don't satisfy this condition? I mean, we really want we won't worry about them, but there is really not much to say about them because those are the modes for which the change happens very, very slowly. If you remember for the pendulum, in that case, really nothing happens to the occupancy levels. Yeah. Okay. So let's see. So actually, that was going to be my discussion here. So just going back to this condition here, we said that there is this effect of increasing the number of the occupancy levels. This happens for only these modes. So what are those? You can basically say that if you assume if the transition or the expansion, whatever, happens on the time scale of the horizon size, so the Hubble parameter, then so that would mean that the delta t would be something like H inverse. Then you can write you can find that the modes here, so 2 pi, right, instead of frequency, write 1 over lambda in natural units. This has to be much smaller than than H, or the lambda has to be much larger than let's see, H inverse divided by 2 pi. So you don't have to worry about 2 pi. You basically see that the modes which are larger than the horizon size at the time of the transition are the ones that get amplified. So for shorter modes, the expansion happens relatively slowly, and this effect doesn't take place. Okay, so the other thing to note is, so inflation, usually when you think about inflation, it's this rapid expansion, everything gets diluted. But that's not true for vacuum modes. And you actually find that the occupancy levels after the transition depend strongly on the occupancy levels before the transition. So the capital NF depends strongly on small nf. And so this is what evades, if you like, this dilution effect that's typical for pretty much everything else in inflation. Okay, so with this in mind, so we basically have written this down. This is telling us how the occupancy levels change in a transition for modes which are larger than the horizon size. And now we can apply it to specific cases, specific examples. All right, so our first example, of course, will be the case where we have transition from inflation to radiation domination. So I don't know if we'll have time to go through the whole thing, but I'll try to at least give you a sketch of how this goes, right? So during the inflation, so phase 1, it will be inflation. And during the inflation, the scale factor A goes exponentially. So we'll have some coefficient d e to the let's see, just ht. H is constant during the inflation. So h here is the Hubble parameter at the time of the inflation, and it's constant during inflation, so we can treat it as a constant, as independent of time. But we have to deal with this in the conformal time. So remember that d eta was dt divided by a. So we can write this as 1 over d times e to the minus ht dt. So we can then solve this and compute that eta is equal to minus 1 over dh times e to the minus ht. Okay, and this d and e to the minus ht gives us 1 over a, so this becomes minus 1 over ha. Or we can solve for the scale factor a of eta, and it looks like minus 1 over h eta. It's kind of a, I mean, if you're If you're used to cosmological time and so on, this looks weird, but you just have to keep in mind that this is a conformal time, scales differently. So this is one solution. So during the inflation, the scale factor in terms of the conformal time does this. In the second phase, we'll have some radiation, and we'll say that happens after, let's see what I call it, sometime T1 or eta 1. So T1 or eta 1 will be the time of the transition between inflation and radiation. So for eta larger than eta 1, we'll have radiation, and there we know that the scale factor is a function of physical time, scales with the square root of time. Okay, so C is another constant here. So again, we need to convert this into conformal time dependence. So you would write down again d eta is dt over a. So you insert a here, ct to the power 1/2. Then you integrate this, and you get eta minus eta 1 because you have to integrate this starting from the transition time, not from 0. So integrating left-hand side gives us eta minus eta 1. Right-hand side, integrating this gives us 2 over c times t to the power 1/2. And this is integrated from t1 to some later time t. So let's see, we can add another c here and divide by c. So this way we have c times time to the power 1/2, that's a. So you can write this as 2a divided by c squared, evaluated these 2 points in time. So we can write this as 2a at some time t divided by c squared minus 2a at t1 divided by c squared. But a at t1 has to be this, right? The scale factor has to change continuously. So I can insert this instead of the a at t1 or eta 1. Right? So I can write this as 2a of t divided by c squared minus 2. And then I write, so this will become plus 1 over, so 2 over c squared h eta 1. And I can solve for a now in terms of eta. And let me write it all out. So that would be eta minus eta 1 minus 2 over h eta 1 c squared. The whole thing multiplied by c squared over 2. Okay, so now I have this expansion or expression for the scale factor in terms of the conformal time, but this c shows up, and I need to get rid of that as well. And one other condition that I can use to get rid of it is to force a dot to be continuous across the transition. So a dot at t1 or eta 1 has to be continuous. So if I express it, if I calculate a dot or a prime derivative with respect to the conformal time, here I'll just get c squared over 2. Whereas here I will get, this will become eta squared, right? So I will have 1 over h times eta 1 squared. So that tells me what c is, and then I can plug that back into here, and I find that a can be written as 1 over h eta 1 squared times eta minus 2 eta 1. Okay, so that will be a of eta in the radiation phase. And by the way we did the calculation, I have already matched a and a prime at a transition. Okay. Why do I care about this? Because I need to go back to the differential equation that drives or that describes the behavior of those various modes, right? So let me write that down again. So we had this equation, if you remember, psi double prime k plus k squared minus a double prime over a psi is equal to 0. So in order to solve this and in order to find the size, which we need to find the Bogoliubov coefficients in the end, we need to know what a is. And we need to find the a double prime specifically, and then solve the differential equation. Okay? Yes? Over here? This one here. Well, because it was written as a of t here. But really, I'm just expressing a in terms of these coordinates. So I've completely done away with t. T doesn't show up anywhere in here. So it's really an expression in terms of the conformal time. Okay, so again, our path here is we start with phase 1 inflation. In inflation, this is what the scale factor does as a function of time. In radiation, this is what the scale factor does with time. Okay, and then I have to go back here and insert a double prime and a, and then solve the differential equation. Okay, so in phase 1, we can write the solution. I'll just give it to you. 1 minus I divided by eta k times e to the I k eta. Okay, and there would be, remember that these solutions come with plus or minus here. I will suppress the negative side, the negative piece, for no good reason. It's just a trick, effectively, to figure out what the Bogoliubov coefficients are. So in general, there would be another term here, which I will suppress. Yes? Why should the derivative of a be continuous? Go ahead. Yeah. Thank you. Okay, so where was I? So we're writing down the solution in phase 1. Let me write down the phase 2 solution as well. This one's actually easier to see because the second derivative of a in this phase will just be 0, right? Because a just scales with eta. So that means this term would be gone, and you will simply get exponential or oscillatory solutions. So in the second phase, this will look like alpha k e to the minus I k eta and plus beta k e to the plus I k eta. All right, so then you have to match the solution again at the boundaries. Psi 1 of eta, psi 1 k of eta has to be equal to psi 2 k of eta, and similarly with the primes, so with the derivatives. All right, I'm not going to go through that, but these conditions then give you alpha and beta in terms of the coefficients in the phase 1, which we've just chosen to be whatever, in this case 1 and so on. So this would give us alpha k is 1 minus I over k eta 1 minus 1 over 2 k squared eta 1 squared, and beta k is 1 over 2k squared eta 1 squared. And that's the piece we wanted, right? Because if you go back to what we wrote for I've erased it here, but you kind of see it. If we're starting with vacuum in the phase 1, then the occupancy level in phase 2 would be beta f squared. So that means that NF, if we were starting with the vacuum in phase 1, would be something like this, and that would give me 1 over 4k to the power 4 eta 1 to the power 4. Okay. And mind you, here f and k are basically the same thing. Okay, so this is the occupancy level, and then we can ask, what does that mean in terms of the quantities we know today? So to do that, we need to do a little bit of gymnastics. All right, so we'll start off with k times eta 1. Okay, that's the piece that that we will be dealing with here. Now, the thing to remember, k here is the co-moving wave vector. So if we want a physical one, we have to multiply it by a with the scale factor. So this will be k physical today. Let's denote that with a 0. And we multiply with the scale factor today, which would be, let's call that a sub 0 as well. And that's multiplying eta 1. Okay, so k can be written as 2 pi times the frequency today. So that would be a times a 0, and then eta 1. Okay, so I have erased this, but let me write it again. So you remember at the end of inflation what we wrote, or for the entire inflation what we wrote, is that the scale factor does something like this. So we can replace eta 1 here with using this expression to something that looks like this. So 2 pi f divided by h, and then a0 divided by a of t1, or of, yeah, let's write it like that. So this quantity here that we're trying to calculate will depend on the frequency today. H is the value of the Hubble parameter at the time of inflation, and then the ratio of the scale factor today and at the time of inflation. So for this, we now need to use a little bit more cosmology. So I will just remind you, we spoke briefly about it on Friday, but if I look at the scale factor, and it's as a function of time, there will be some inflation piece, there will be expansion that goes as t to the power 1/2 in radiation domination, and then there will be t to the power 2/3, and this will be the matter domination. So this would be the present time. This would be what we call the time of matter radiation equality. And then we're trying to look at what happens here. So the scale factor here can be expressed. You see that it scales as t to the power 2/3. So we can, in the matter domination, so we can take that piece and then multiply it with the corresponding scaling factor in the radiation domination, which goes as t to the power 1/2. So let me write that out. This will become 2 pi f divided by h, and we'll have t0 divided by t at the time of the matter radiation equality. So that's this stretch here, and it goes as t to the power 2/3. And then we have the second piece from the matter radiation equality to inflation, and that goes as t to the power 1/2. All right, so the nice thing about this is that some of these things are known. So this in particular is basically approximately equal to the redshift of the matter radiation equality. Okay, so this is because of the expansion of the universe. The wavelengths emitted at this time get stretched, and what we observe today is slightly, actually in this case, substantially larger wavelength. And the stretching can be described with kind of a Doppler shifting parameter, which we call the redshift in cosmology, and we write it typically with z. And in this case, for this particular value, this is about 3,000. So we can plug that in, and we can redefine, let's call it f1, h divided by 2 pi times z equality, and then this times this piece here, which is t1 divided by t equality to the power 1/2. Okay, so this is a new parameter that I'm defining now, and in terms of that new parameter, I can write k eta 1 as just f divided by f1, right? So k eta 1 is just f divided by f1. And if I take that and plug it in here, then I can find that the occupancy level is just 1. Okay, let's rewrite it again. So it's 4k to the power 4 eta 1 to the power 4, and that gives me f1 to the power 4 divided by 4f to the power 4. Okay. Let's see, how am I doing with time? All right. All right, so we have this piece now. So that tells us what happens to the occupancy levels. How big is this quantity f1? Well, you can get a sense of it relatively easily. So specifically in radiation domination, h of t scales as goes as 1 over 2t. So you can replace t1 with 1 over 2h, where h again is the Hubble parameter at the time of inflation. And if we plug that in here, what we find is that f1 is about 10 to the power 9 hertz, but for a specific choice of h. So here I chose 10 to the minus 4 times the Planck mass. And it goes as a square root because there is a square root in here. So if, and this is in hertz. So f1 is, of course, it's a frequency, so those are the right units. If you choose that the inflation Hubble parameter is something like 10 to the minus 4 of the Planck mass, which, I mean, it's a guess, we don't really know, then f1 is of order 10 to the 9. Okay, so we know what happens here, but what we really care about in our searches is what is the energy density. And to compute the energy density, we write something like this. So we basically integrate over the phase space. So this is d cubed k divided by 2 pi cubed. And then I have to write the density of modes in each cell of this phase space. So it will be a function of k. And then what is the energy of each of these times the energy of k. And I have to put in a factor of 2 for the two polarizations. Now this turns out to be relatively simple because we found that the density here is just n capital N sub f, right? So we could write this as capital N, and then since we don't, the energy will not depend only on the frequency here or the magnitude of k, we can write this as omega h bar, right? So we can write that as 2 pi f h bar, which is 1. Okay, so that let's see, we can rewrite in a slightly different way. Let's see, we have the 4 pi, which I will put out front, and then I will. Is there a question? Sorry. Yeah. That's right. That's right. That's another way to see it. Yes. Okay, so over here, I'm going to now rewrite this in terms of frequency. So there's a factor of 2 pi that goes with it, and since there's a cubic here, there will be this 2 pi to the third will go away. So I can write this as an integral. Okay, and let's see, d cubed f, if you like, times nf times another f here. This will give me another 4 pi, so I have 16 pi squared times the integral of df of f cubed and f. And really what I care for, remember we take the derivative of this relative to log frequency, so let me rewrite this as 16 pi squared integral d ln f, and then this will be f to the power 4 and f. Okay, so we're almost out of the woods. Okay, so now we're finally trying to write down what is the energy density omega, which, as we said before, we write as 1 over the critical energy density today times d rho GW d ln f. And this derivative we can now read off of this last line. So we can write this as 16 pi squared n sub f times f to the power 4 divided by rho critical. Okay, but we know also what n sub f is. It is here, f1 to the power 4 divided by f to the power 4, and then another factor of 4. So this will become 4 pi squared, and then we'll have f1 to the power 4, and f to the power 4 will get cancelled by this f to the power 4. Okay, so we lose frequency dependence, and that's it, right? We only have the rho critical here, which now putting in all the other constants, so we have 4 pi squared. We need an h bar, f1 to the power 4, and rho c times the speed of light cubed. So we know all of these numbers now. We know what f1 is. We can compute what the critical energy density today is. It only depends on constants like the Hubble constant and g and so on. And so omega GW, which is a function of frequency nominally, is actually not dependent on frequency. It's 10 to the minus 13 if you put in if you put that the Hubble scale or the Hubble parameter at the time of inflation is 10 to the minus 4 times the Planck mass, and that's squared because there's a fourth power here and there's a square root here, so that gives us a square. So the upshot of this is that the energy density in this particular quantity, omega, so a normalized energy density in gravitational waves due to this process gives us a flat energy spectrum at a level of about 10 to the minus 13, and that goes on for all modes for which the occupancy level is smaller than 1, which is for frequencies smaller than about a gigahertz or 10 gigahertz or so. Okay, that's basically our story here. This is how you would compute the gravitational wave background from the very early universe. There are wrinkles, so not wrinkles, but modifications or upgrades or updates, whatever you want to call them. So, for example, we know that that this radiation phase is followed by the matter phase. So you could repeat the same thing using radiation to matter. So you can now say that phase 1 is radiation, and then phase 2 is matter domination. So then you go through the same process. You solve for the A, the scale factor, in radiation domination and in matter domination in terms of the conformal time. Then you again plug into the equation that we derived that comes from the Einstein equation that drives or describes how the modes behave as a function of time. That will give us solutions in phase 1 and phase 2 for those psi's. And then we use those solutions, we match them basically at the transition to find the Bogoliubov coefficients that connect the expansions in the two phases. And once you have the Bogoliubov coefficients, you know what n is, because this is just beta squared, right? One of those coefficients squared. And then you follow through the same argument here to compute the energy density. And what you find is that omega GW of F in that case looks something like this. So it's about 10 to the minus 13 times F equality. This is the frequency at the matter radiation equality divided by F squared. And then you need to again assume something for the inflation scale. So the Hubble parameter at the inflation, we again assume it to be 10 to the minus 4 times the Planck mass. And you see that this is different. You can compare. This is for the inflation radiation phase. This is for the radiation matter transition. And there is this F squared dependence. You can also find which frequencies or which modes are this kind of effect applies to, and it applies only to those modes for which which are larger than the horizon size at the radiation matter equality. So that turns out to be frequencies smaller than the frequency corresponding to the scale of the matter radiation equality, which is about 10 to the minus 16 hertz. So you can put these two together and you get something that looks like this. So this would be frequency and omega GW, and it looks something like this. It goes as f to the power minus 2 at frequencies below 10 to the minus 16 hertz. And then it's flat all the way out up to the highest frequency, as we said, was about 10 to the 9 or 10 to the 10 hertz. Also, this whole business doesn't even make sense if you look at the modes that are larger than the horizon size today. And the horizon size today is basically given by the Hubble constant, or the value of the Hubble parameter today, which is about 3 times 10 to the minus 18 hertz. So if you make this with the assumptions we have made, nominally that h is constant during the inflation and so on, we get this kind of behavior f to the power minus 2 at very low frequencies, which apply in this frequency band, and then it's effectively flat across above that up to a gigahertz or 10 gigahertz. So this is a spectrum that we expect the primordial fluctuations in tensor modes to look like today. Okay? Any questions on this? Everybody okay? All right, so I'm done with writing. You, yeah. Yes. It's all quantum mechanical. Yeah. So I guess I should turn this on. So the spectrum will look like this, but you see that it scales with this h here. Another way to put that is it depends on how many, what was the amplitude of the primordial fluctuations that you started with. And we don't know the answer to that question. What we do know is what basically the CMB measurements tell us, and that basically tells us what the amplitude of the scalar perturbations was. Uh, um, so um, so to answer your question, we really need to know what is the ratio in the amplitudes of the tensor and scalar perturbations in the early universe, right? And that's what's usually referred to as this R coefficient. You may see it in some of the CMB papers, for example, and cosmology papers and so on. And that's basically setting the scale here. So zero perturbation, there would be, if R is zero, meaning that there were no tensor perturbations, none of this, I've just wasted my time and yours. It basically will go through here. It defines the energy content at a time, which defines the evolution. So this is kind of what I wanted to talk a little bit about. So this is again energy density versus frequency, and this blue curve is the inflationary model. It's a step up relative to what I've done. What I've done here is assuming that h is strictly constant, so the Hubble parameter during inflation doesn't change. In the slow roll models of inflation, which I briefly mentioned on Friday, that's not strictly true. So the h does change during the radiation, which results in a bit of a slope as a function of frequency. So you see that this is basically flat above 10 to the minus 16 hertz, and you have this f square dependence below. There are several experimental limits shown here to guide your eye. The CMB is an upper limit based on the measurements of the lowest multiple moments. So it's basically a result of Kobe, slightly updated now. This is over here is the LIGO result. These are some indirect limits from Big Bang nucleosynthesis and the CMB and large scale observations and so on. This is where LISA is hopefully going to be. This is where we expect the design sensitivity of LIGO and Virgo to get us. These are the most recent pulsar limit observations, I think. So as you see that we're not going to get here. Even the third generation of terrestrial detectors, I mean, there is a lot of discussion about them now, what exactly they will look like and so on. They may get us here or maybe here, depending on what we exactly do. But getting to this level is very, very hard. So you may ask, so why do you bother with this? Well, one thing is that this is a very important source, so we don't want to lose it from our thinking. But the other thing is that there are other things that we have not discussed, and there are many additions or wrinkles, as I said before, that we can add to this model, which can change things dramatically. So these changes could be within the inflation, they could be at the end of the inflation, it could be after inflation. And remember, this is all before first minute runs out, right? After the Big Bang. We don't know the physics, so there are lots of models and lots of things that people are talking about. So, for example, let's say we think about the inflationary model. So this is, we're still talking about just what happens during the inflation. One way to ensure flatness of the potential, of the inflaton potential during the inflation, is to impose a shift symmetry. So if I add a constant to my field phi, the potential doesn't change. And one way to achieve this is to assume that the inflaton potential is an axionic field. So if you don't know what that is, don't worry about it. Basically, I mean, there's a lot of literature. There's some people who have looked at this, and there's a lot more who have studied these kinds of effects. Basically, what you end up with is you can have a Lagrangian that describes the interactions in this kind of a model. that looks like this. So it has this axion inflaton field phi, and you introduce some gauge field. So there's some coupling of the inflaton to some gauge fields. If you go through the calculation, you figure out what is the dispersion relation for these gauge fields. It looks like this. So typically, you know, a photon would look like that, right? But instead, here you have a correction factor that depends on the scale factor A, which during inflation grows exponentially, which means that one of these two modes will become tachyonic faster than the speed of light. So only one of these two helicities survives, and that's kind of interesting because, as we'll see in a minute, it means that only one polarization of gravitational waves is produced. And there are two other things. So first, the Lagrangian supports an interaction of this kind, which means that two of these gauge fields can combine to give us the inflaton field, which then effectively extends the inflation, makes the inflation run a little bit longer. And the other thing is that the gauge fields can produce the gravitational waves, and they do that, as we said before, in a polarized way. So only one polarization will be produced. And in addition, they do it preferentially at relatively small scales or high frequencies, which means that if I start with this blue curve at relatively high frequencies, I can have a boost in gravitational wave production simply because this is a second mechanism for producing gravitational waves that I'm adding to my model. Namely that the gauge fields that I have thrown into my model are now interacting and producing both the inflaton field and the gravitational waves. Yes? You mean this? Yeah, you're right. I should have cut it off here, or roughly here. Yeah. Okay, so I believe you get one of the two, either plus or across. I mean, of course there's a definitional thing, right? But it won't be circularly polarized, if I remember well. Yeah. 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 So that's a definitional piece, right? What's the physical mechanism? So nominally, you would have two modes, two polarizations of the gauge field, and they would result in two polarizations of the gravitational waves. Ah, that's a good question. I'm not sure. I'm not sure exactly how this is defined. I mean, you can, if you're looking at a particular direction, you can have a combination of two polarizations coming in or not, right? So it is possible that the polarization will be different in different directions, but it will still be a single polarization. Is that what you're asking? I'm not sure. So what I'm saying is that from a given direction, you will only see one polarization of gravitational waves coming in this model. For each, for each, I think for each frequency you would get, yes, for each frequency you would get one same polarization from a given direction. Oh, yeah. I would have to think a little bit more about it, but I think in the end, let's leave it for later. I'm not entirely sure, to be honest. I believe that the entire spectrum ends up being polarized one way. Yeah, so, okay, we can talk more. Okay, so that's one example of kind of an addition to this baseline vanilla slow roll inflation model, adding additional physics that during the inflation can change things. Another thing that can happen is, oops. So the inflation has to end some way, and as we said before, during inflation, whatever was created, whatever particles may have existed before the inflation, they all get diluted away because of this huge expansion. But of course, we know from observations that we have a lot of stuff around us, right? So all of the regular particles had to be somehow created at the end of this inflation. And this process is typically called reheating. Somehow the energy from the inflaton field has to be transferred to regular particles. And that means that you have to have a specific particle physics model in place, which will allow you some sort of a coupling of the inflaton field to other particles. And there are many of those in the literature. Some of them turn out to be non-perturbative and have resonances, and they call by the name of preheating. So there's also a number of people who have studied these effects. Basically, I'm not an expert on these, so my understanding of them is that when you have an inflaton potential like so, towards the end of the inflation will kind of slosh back and forth, oscillate around the bottom of the potential. And at each time it hits the minimum, it will produce whatever particles are being coupled to it, bosonic, fermionic fields, and so on. And in some cases, you can set up a resonance so that these bursts of production essentially result in an exponential increase of, let's say, a bosonic field. That means that you will have large field gradients, meaning large stress, meaning gravitational waves. So to do this, you end up essentially having to do a simulation, and there are people who have done these. There are results in the literature. Typically, what you find is that this has to happen at a relatively high energy because the inflation ends at a relatively high energy, and the corresponding frequencies of these of the gravitational waves produced this way are relatively high. But there are models of, let's say, hybrid inflation and so on, which could bring the inflation energy level down to something like MeV scale, and that could be more interesting to the existing detectors. So the spectra for these models looks something like this. This is, if you believe these models, this is probably something that's a bit more realistic. But in some cases, maybe you can bring it down to frequencies where the terrestrial detectors operate, or maybe LISA even. So these kinds of extensions would be relatively difficult to obtain, simply because we don't have detectors at such frequencies. Then after the inflation, as we said before, there is very little we know about what happened prior to the Big Bang nucleosynthesis. So it is possible that there were additional phases in addition to inflation and radiation and matter phases. There may have been additional phases in the evolution of the universe, depending on what else exists in terms of the particle spectrum. So this slow roll model, where the slope of the spectrum, which was almost zero, R here is that tensor to scalar ratio, this doesn't necessarily have to be true, and in fact, we really should go out there and measure it to check whether the inflationary models really follow this kind of a behavior or not. So the if in particular, if there were some additional phases in the evolution of the universe, you might get another transition, right? And in that, during that transition, you may change the spectrum of the gravitational waves that are being produced as we've seen them today. So there is a very nice paper by Latham Boyle and Alessandro Buonanno. They have looked at the situation and basically asked, so what happens if you have another phase with a relatively stiff energy density? With a relatively, stiff energy density, right? So basically what this means is that if you write that pressure is some W times rho, where this will be the equation of state parameter W. For matter, that's just 0. For dark energy, we believe it's -1 or thereabouts. For radiation, it's about 1/3. If you assume that there is something that's even stiffer, so that a small change in the energy density gives you a large change in pressure, then you might get a boost that looks something like this. And in fact, they have given a general relationship for the energy density in gravitational waves. It turns out to look like a power law. Here is the usual NT that is basically 0 in the slow roll model, plus some function of this W, the equation of state parameter. So whether this is possible or not, we don't know, but we can measure it. In fact, you can take the measurements of LIGO or LISA or pulsars and basically constrain these parameters, the NT and W. And this is an old plot from one of the older LIGO search, stochastic search papers, but basically shows that in this plane you can exclude some of the models out here, and that that allows us to basically say something about what kind of behavior the early universe could have followed in those epochs at least. Any questions? Yeah. Seems like it is. I mean, I'm not an expert on this. Why do you think it might violate causality? If it exceeds 1. But it does not need to be 1, right? Whoops, sorry. So radiation is 1/3, so there is some room. Yes. Yep. Yes. Yeah. So this curve here assumes the latest, well, maybe not the latest anymore, but an upper limit on the R factor, the tensor to scalar ratio. So that bumps it down below this level. Yeah. Well, it actually ends up not working like that directly. No, it doesn't scale directly. There's kind of a pivot point here, and the terrestrial detectors happen to be kind of close to that pivot point. So pushing this down also means that the slope is not as bad. So you end up being roughly at the same level. So in maybe first order you would be right, but then there are these subtleties that make it be not as bad. So the dependence of the amplitude here in the over here, I guess I should, or anywhere in this region, is not very strongly dependent on R. Mm-hmm. Yeah, I think that's the best probably case for this particular model. What people refer to as the amplification of vacuum modes. But as I was saying, that's just one mechanism that we expect to have then coming from the early universe. There are many things on top of that people have proposed, and I'm just kind of sketching them out now. So there could be significant boosts, like in this case. Yeah. Yeah. That's right. So some of the simplest, there is, I think that some of the models have been ruled out, but there's a lot that haven't. So in short, that would be the assessment. The simplest ones, like phi to the power 4, I believe has been excluded. I believe some of these hybrid inflationary models are under stress as well. These are models that allow you to bring the energy level of inflation relatively low. But there is plenty of models that are still consistent. Okay. All right. So a few minutes. So I'll just touch on a couple other things. So one of these is goes under the name of phase transitions, and roughly speaking, the idea is something like this. So at very high temperatures, earlier in the evolution of the universe, when the universe is very hot, the details of the the details of the of the potential, or what exactly happens at the bottom of the potential, they don't really matter, right? If you look from very far, this may as well just be a simple kind of harmonic oscillator potential. But as the universe cools down, you get into this this regime here, and you then start to fall into the true vacuum states of this potential. So this is an analogy that people sometimes bring is, you imagine you have a pot of water and you cool it down, it will start to freeze at some point. But how will this freezing happen? And typically the ice starts to form in different places, and then the crystal starts to grow. So it's a similar idea here. You have you have some sort of false vacuum early on, and as the universe cools, you have nucleation sites where the true vacuum starts to form. And those sites start to grow, essentially like bubbles, and they can grow very fast. Depending on the model, they could be growing at basically the speed of light. So then you imagine these bubbles basically growing really fast, and eventually they collide with each other. And when that happens, there will be perturbations in the plasma, and various maybe turbulences being set up. And those processes could create gravitational waves as well. This kind of description is what we call the first order phase transition. So it's the relatively violent kind. There's a second order as well, which is smoother. And we know that at least two phase transitions happen in the early universe. One of them has to do with the Electroweak symmetry breaking. We know that the Higgs potential is basically has this kind of behavior that I showed on the previous slide. So when this Electroweak symmetry breaks due to the Higgs potential, we have the traditional standard electromagnetic and the weak nuclear forces, and that happens at about a TeV scale. Based on the standard model of particles, if that's all there is, this transition would be second order, and it would be much smoother and probably would not give us much in terms of gravitational wave production. Another transition is the QCD phase transition, and that one is also expected to be second order based on the QCD lattice simulations. But in both cases, there could be new physics that can change this. And then there are also additional possible phase transitions that may have happened. In all of these cases, there will be some new physics, either because there's some large extra dimensions out there, or dark matter models where the dark matter only gravitationally couples with the ordinary matter, so at some point it has to decouple, and so on. So this is another area of active research. There's a very good review, I guess you could call it a review by Caprini et al. They summarize the situation. Basically, there are three dominant models for production of gravitational waves in these first order phase transitions, from collisions of bubble walls, from sound waves that are set up in the plasma as these bubbles walls sweep through the plasma, and then the magneto-hydrodynamic turbulence that also could be set up in the plasma. And the spectral shape then depends on a bunch of parameters. It depends on how long the phase transition lasts. It depends on the Hubble parameter at the time of the phase transition, just like what we saw in the inflationary models. Temperature, the phase transition, bubble wall speed, and also how much energy density is in the form of kinetic or the vacuum or the radiation energy, how that's being split between the different components. So this one is probably the most interesting, the Electroweak phase transition, because if you go through the math, the TeV scale, energy scale, corresponds to the LISA frequency band at about tens of millihertz or so. But there are tails. So these are some cases. I don't have time to go through them, but examples of spectra for some choices of the beta, H star, and other parameters. And what you see is that the spectra are typically fairly broad. They have a peak, but the peak is relatively wide. And depending on the situation, that peak could be sitting right in the LISA band, or somewhere between LISA and the terrestrial detectors, or maybe even in the terrestrial detector band. This is basically an example of where probing different frequencies will be really useful. So this is a recent paper that I was involved in as well. This is showing parameter space for various cases and so on. We don't have to go into the details, but the upshot is that gray is what LISA can explore, and black is what the Cosmic Explorer, so this would be the third generation terrestrial detectors, could do. And combining those, you could explore more of the parameter space. Or in some cases, they could overlap. Yep. No, so in these studies, we basically ignore that there is any astrophysical stuff that will hide things. That's a whole other problem that you're absolutely right, we'll have to deal with. Might not see anything because of it, but that's yet another problem. Okay, last thing I wanted to mention, and I'm basically out of time. So these phase transitions in the early universe could lead to topological defects that we call cosmic strings. Strings could also be fundamental strings, blown up to cosmological scales. Either way, if they existed, they could basically fly around the universe, and if they intersect each other, they could create loops. So you could have two strings that intersect at 2 points, and you have a loop, and then two other open strings. Or you could have a single string that just intersects itself at 1 point and creates a loop. And these loops then are expected to emit gravitational waves and basically decay over time and disappear. To fully describe this, you have to basically make a numerical simulation of what this network of strings looks like, starting from the largest scales to the smallest scales. And the details are really complex, and the various calculations don't necessarily agree very well. There is a book on the topic that's somewhat out of date at this point, but it's a good starting point if you're interested in the topic. So as far as the gravitational waves are concerned, you could have these kind of cusps or kinks on the strings, and they would produce gravitational waves, and especially if they're boosted relativistically in the direction of the Earth, then we would observe bursts of gravitational radiation. And there you can search for this. You can search for these kinds of bursts, or you can add up the contributions across the entire string network, and then you get a stochastic background because you have just many of these uncorrelated contributions. So this model is actually an interesting example because the gravitational waves would be produced throughout the history of the universe. So they could be produced very early on as well as yesterday. And that makes them different from all the other cosmological models we talked about, because basically everything else was something happened in the early universe in the first minute or whatever, and it's done. We're just observing it now. This one is a little bit different, and this is an example of a spectrum that you could get from these cosmic string cusps or kinks. It's typically flat in the terrestrial band, and depending on the parameters of the model, it could start to increase at relatively low frequencies, and that increase could also be somewhere down here. There's a lot of variation. So there is this is from a recent LIGO-Virgo result paper. We looked at 3 different models, and these 3 different models are basically treating the distribution of the sizes of the loops in 3 different ways. There's one that's relatively old reference. This one tells us the loop size at the formation, and this one tells us not just the size of the formation, but at any given time gives us the entire distribution. And we have basically taken these models, scanned the parameter space, and looked at which parts of those parameter spaces are ruled out by the upper limits on the stochastic background or by the burst searches and so on. And as you can see, a lot of the parameter space is already ruled out. In fact, for this third model, M3, it's already all out. The shades of gray here are the LIGO, stochastic, and burst searches, and then there is also the pulsar bound and the CMB and BBN bound. So these are these dashed curves or dotted curves. As you can see, a lot is already excluded. So this particular one, I think, is the most excluded by the pulsar bound, and that tends to be the strongest in basically all cases. But there is some room to maneuver over here in this model too. So if you trust this, at least the parameter space that's shown in these plots is almost all excluded. You can ask, well, what happens if I take the string tension to be smaller than whatever, 10 to the minus 12 in this case? You can do that, but it becomes less and less cosmologically interesting. So I think that's all I have. Yeah, that's it. So we will be doing, of course, the cosmic string searches in the future, but at this point, it doesn't look very good for them. All right, that's it. Any questions? Yes. Effectively, yeah. So so the lowest multiple moments of the CMB are effectively in this region, very close to the horizon size today. That's why they're limited, or that's why their signal would look like this. You mean here or in these plots? So if the scale of this will depend. Remember, this is just a model. And it's a model assuming very specific behavior of, for example, the Hubble parameter during the inflation has to be constant and so on. So with that kind of assumptions, and with some choice of the scale at which this happens, I get a curve. But I can change these parameters. I don't know what they are, and all of this could be an order of magnitude lower. And this is the CMB is basically telling me what's the highs that I can have, but I can certainly have lower. I could have nothing. It, for this model, yes, but if I change the model, anything is possible. Yeah, 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 that's right. Bruce, did you want to? And are coming back later. Yes. So if CMB experiments could measure this rather than put an upper limit, then it would limit the parameters of this particular model. It wouldn't necessarily be able to tell you, oh, this is the model, because there may be multiple models that could fit that experimental data. But then you could combine this with maybe a LIGO or a LISA measurement at high frequency, and that will be very powerful. Well, the gravitational waves, if we could see them, I mean, they would be essentially unperturbed since then, right? So that would be as direct as you can get.